Good evening, everybody in Taiwan. We're very happy to have Professor Tatsuhiro Yokoyama-san from Kyoto University to give us a talk on the within the of the low latitude ionospheric research working group seminar series. If you look at the Professor Yokoyama's CV, it is really amazing. Firstly, he graduated from spent all his undergraduate and graduate studies at Kyoto University. He got his PhD in 2004, which is about 20 years ago, from the Graduate School of Informatics at Kyoto University. He is an expert on ionospheric plasma physics, of course, and he has done a lot on numerical simulation and the analysis of plasma instabilities. But I would say, most importantly, he won a lot of very prestigious awards for young scientists, just including in 2006, the Inoue Research Award for Young Scientists. I think it is given by foundation, Inoue Foundation of Science in Japan. And then Obayashi Award in 2007. And then in 2012, he got the Kospa-Seldovich Medal, which is a very prestigious medal for young space scientists. And then just 2 years ago, he won the Nishida Prize for Promotion of Geo and Planetary Sciences, given by the Japan Geoscience Union, JPGU. So it's already made, Yokoyama-san. Okay, we would then listen to your very interesting lecture. Thank you.
Okay, so thank you for the nice introduction. I'm Tatsuhiro Yokoyama, Kyoto University, a research institute for sustainable humanosphere. I'm mostly working for the ionospheric irregularities, like so-called equatorial plasma bubbles, are often observed in the lower ionosphere, lower latitude and equatorial ionosphere. Then today's topic is our observation and the numerical simulation studies of these equatorial plasma bubbles. So this is the contents of today's talk. Some introduction and the observation. I focus on the observation by our facility in Indonesia called the Equatorial Atmosphere Radar in Sumatra Island. Then some numerical simulation studies of equatorial plasma bubbles, then some summaries. So this is my background as introduced by Professor If. I graduated Kyoto University. Now there is, our institute is called RISH, but its former name was RASC, Radio Atmospheric Science Center. My advisor was Professor Kao. Then moved to Nagoya University and working with these colleagues, then in the colleagues in the US, and back to Japan in the Kyoto University and the NICT. Their groups are working for the operational space weather services in Japan, collaborated with several international institutes. So this is the topic on the ionosphere. Maybe this importance of ionospheric research is already known in this your audience. But as you know, the ionosphere is a path of radio waves. Recently, this GNSS satellites signals must penetrate into the ionosphere to reach the ground. Then the propagation delay or scintillation in the ionosphere, it becomes serious problems in the recent years. Because recently we used the GNSS services to the positioning and the navigation. The accuracy is getting very precise. We can use this technology to monitor, to measure the current position with the error less than like centimeter scale. Estimation becomes possible. But which also means the error during the propagation of radio waves in the ionosphere or atmosphere becomes more important. So we have to remove the error due to the ionosphere or water vapor in the atmosphere. This is a very important topic to utilize the very precise positioning and navigation services. Then one of the important, one of the serious problems is the scintillations of the radio waves. This is caused by the ionospheric irregular structures driven by several plasma instabilities. The one of them are well known, the spread F phenomena in the ionosphere. Well, this is the review paper by Dr. Uthman, published in 2009, already more than 10 years ago. Well, in the abstract, he said that the spread F was observed for the first time as an abnormal ionogram in Francayo about 70 years ago. So now it's already more than 80 years ago. But only recently are we coming to understand the physical mechanisms responsible for its occurrence and its capricious day-to-day variabilities. So we know that the basic mechanism to drive the spread F, but it is almost impossible to forecast the occurrence of spread F day-to-day basis because it is very unpredictable. So it is very seriously, very difficult to make a forecast of the spread F occurrence. So this is a very first image of the spread F in almost 100 years ago, almost 90 years ago, in Peru. So this is the reason why the mechanism phenomena is called spread F. So this is a normal trace from the ion zone, but sometimes we see this spread echoes are returned. So that means the ionosphere is not uniformly stratified, but it contains very irregular structures in the ionosphere. After several years, several decades, now we come to know some more clear picture of the ionosphere. Then the phenomena is start to be called the equatorial plasma bubbles. So now there is some perturbation in the bottom side ionosphere, then making some bubble-like structures. Then this structure is going to penetrate into the top side, like air bubbles in the water. Then if there's a view from the west or east-west directions, so this is north-south meridians. So this depleted low-density regions make flux tube depletions. Then it come to the northern side and southern side. Then the impacts of the radio wave propagation is not limited over the equator, but it's distributed in the wide latitudinal coverage. And this is a radar observations and the satellite observations simultaneously. Then when we have a strong radar but scatters, then satellite, this time the AEE satellite goes through these structures, then the density is sharply dropped inside these radar echo regions. So this is good evidence that actually these bubble structures are going to the ionospheric top side. So the image is like that. So the bubble structure is going to the top side, then satellite measure the low density regions when the satellite penetrate into these low density regions. So the basic theory is already well accepted. This is called Rayleigh-Taylor instability. So this is a view in the equatorial ionosphere. If we have some density perturbations in the bottom side, then assume that like a gravity or neutral wind drive this current to the eastward. Then there are the charge separation happened, and the positive charge here and the negative charge here and here. Then that makes up local polarization electric fields, delta E. And these regions, delta E directed to the eastward, then that makes delta E equal speed drift upward. So this region, the lifted regions have a further move to the upward, and this region is going to downward. So the initial perturbation is enhanced by this mechanism. And in this case, this process makes unstable structures. On the other hand, when the background density gradient is downward, then this polarization effect is going to stabilize the initial plasma density perturbations. So in this case, the structure, this mechanism becomes stable. So essentially, the linear theory suggests that the radiator instability becomes unstable only the bottom side of the ionosphere, where the plasma density background gradient is upward. The top side ionosphere, where the gradient is downward, this theory doesn't work. It becomes stable. But the result, observational results, is that the top side is also unstable structures, unstable. The irregular structure of the field, even in the top side. So this is the reason why this plasma bubble concept is proposed. So this bubble concept can explain that the low density regions penetrate into the top side, and that makes the unstable structures that produce these strong radar backscatter echoes. So this is our facility. This is not in a lower latitude one. This is our near our campus in Kyoto. It is called MU radar. So this MU radar was built in 1984, almost 40 years ago. This is a big radar, mostly targeted to the MSD regions in the middle and upper atmosphere radar. So many elements, Yagi antenna elements, 475 elements, 1 megawatt peak transmitting power. Then we built the similar type of radar in Indonesia, which is called equatorial atmosphere radar. Was built in 2001. It's over 20 years ago. This is also similar active phase array type radar, but peak power is less than the MU radar, 1/10 of the MU radar transmitted power. But we have a 560 elements array. Then there's steerable radar, and this is used for the observation of the lower troposphere, stratosphere, and atmospheric observations. Now, this is a picture taken by the drone a few years ago. This is a radar antenna field. Then the instrument is stored in this building. In the nearby regions, there are several collaborators. For example, the ionized tower antenna here installed by NICT, and also the VHF radar by Nagoya University. Then different instruments are also around this radar site. Then this equatorial atmosphere radar location is exactly the geographic equator, but from the magnetic equator, it is a little bit about 10 degrees south from the deep equator. So magnetically, it is located about in the lower latitude station around here. The magnetic equator is located here. And observation by the EAR for the atmospheric irregularities, the radar beam is directed to the perpendicular direction to the geomagnetic field lines. So observed regions are around here and here. In the E region observations, we are observing this region. The F region observation is around here. Then these regions are connected to the magnetic equator. The apex altitude is connected in this relationship. So the E region measured by the EAR is connected around the 280 kilometers over the equator. Then the F region around 300 kilometers measured by the EAR is connected to the 520 kilometers over the equator. Then the radar beam can steer the direction from east-west directions, then covered plus minus about 300 kilometers in the east-west directions. Then we can steer the radar beam very quickly. Then we can get the two-dimensional radar backscatter images every 20 seconds. Then we can measure the plasma bubble growth with very high time resolutions. This is some typical events measured by the radar. We are showing the three beam directions: east direction, south, and western side. Then this color code shows the signal to noise ratio. Then the bottom panel shows the line of sight Doppler velocity. Positive value means toward the motion toward the radar. Then the negative color means the away motion from the radar. So in the very beginning of the plasma bubble formation, it shows a strong away motion or upward motion. So it means negative Doppler velocity means the very rapid growth of plasma bubbles moving to the upward. Then the radar is sensitive to the 3-meter scale irregularities. It's the half of the radar wavelength. So that means inside the plasma bubbles, we have very small scale plasma irregularities are located in these regions. Then this is the local time from, this is written in the UT, but it's about 8 p.m., 7 or 8 local time, then disappeared around midnight. Then very less echoes until the morning time. Then because we have multiple radar beams, then we can combine these multiple radar observations to make this type of movies. So this one snapshot is taken every 20 seconds. It covers from about plus minus 2 degrees or like 200 or 300 kilometers. And this is the altitude. So in the very beginning, radar echoes grow very quickly, then moving from western side to eastern side. So coming into the field of view from the west side, then move away from the east side. Okay, this is the very beginning. Very strong echoes quickly grow, then enter from the western side, then escape to the east side. So this is a very typical motion, typical time series of the plasma bubble formation, then decayed around midnight. So this is a picture from another day, but you see this is the time and altitude. Then we see like 4 radar echo clusters. The very first one is close to the sunset. So this line indicates the sunset time in the local region on ground level. Then just after sunset, we see a very strong echoes. But this is the kind of kilogram of the echo intensity. So this is the time, and this is a slice along the east-west directions at 300 kilometers. So the cluster A start to appear within this radar field of view, which means that these cluster A bubbles are generated within the radar field of view. So we say this is like a fresh bubbles here. But this cluster B, about 1 hour later, these echoes are entered from the western edge of the radar field of view, then move with a very constant velocity, then going out from the eastern side. That is the same, the cluster C and D. The cluster D entered from the western edge, then decayed over the radar side. So this is a very typical motion of the radar echoes. So only the echoes just after the sunset are generated within the field of view, but others are kind of fossil type, generated in the different place, then coming to propagate over the radar side. Then we categorize into 2 types. The first one is the fresh plumes appeared over the radar side. The other case is only fossil types are observed. So both cases are the bubble day. I mean, the bubbles are observed by the radar. But the first type, the fresh plumes are observed over the year. In this case, this graph shows the H-F at 2.5 megahertz measured by the ionosphere in the radar site and in the magnetic equator site. So these cases, this left case, the ionospheric height is increased very quickly. But this side, right-hand side, only when only fossil plumes are observed, then this ionospheric height rise is not so strong. So this height rise is driven by the eastward electric field, so-called the pre-Barson enhancement. Well, this is a key factor to drive the plasma bubbles. So when the bubbles are observed over the radar site, the fresh case, then the ionospheric height is increased very sharply. So this is a very key factor to control the plasma bubble occurrence. This is another measurement, GPS scintillation measurement by Nagoya University Group. This is also the very long period observations since 2003. This is from January to December, 1 year observations, from 20 local time to midnight. Then the red color means the strong scintillations. So within a year, this is well known that the scintillation occurrence is very often in the March and September equinox seasons. It's going to decrease with solar activity decreasing. There are almost no scintillation in this solar minimum period, 2007, 8, 9, 10. Then scintillation back to normal after 2011 when the solar activity is going to the maximum. So this is a scintillation activity, it's a very typical one. A strong solar activity, positive correlation with solar activity, and the peak occurrence in the March and September equinox. However, our radar was operated also in the solar minimum period in 2009. In 2009, there's almost no scintillations throughout the year. But we can get the radar echoes into 2009, May. But the radar structure, echo structure is very different from the typical plasma bubble type. Like a downward more slopes, then occurrence is around midnight or after midnight. Very low occurrence in after sunset time. So this picture is something similar to the observation by the MU radar over Japan, like this downward slope or this upward motion and downward slope. These type of echoes are observed over the MU radar. So during the solar minimum, this type of echoes are kind of a mid-latitude type phenomena, or maybe occurring over the low latitude regions. Then again, this period there's no scintillations. No scintillation, but we can detect the radar echoes. So this is also something different point from the typical plasma bubbles. Again, this is a 2D plane plotted in during this low solar minimum period. This is this case we see this kind of slope, and these slopes are tilted from northwest from like these slopes. So this is something similar to the medium scale TIDs over Japan. So this is somewhat similarity to the mid-latitude phenomenon. So this is the second event during the solar minimum 2009 the July observations. So this case, this is also different from the typical bubbles. It's start to grow around midnight, then slowly move into the westward after midnight. So during the solar minimum, maybe these phenomena are somewhat different from the typical plasma bubbles. During that day, we have a simultaneous observation with the CNOVS satellite. A radar was observing these southern and southern hemisphere. The CNOVS are flying in the northern hemisphere along the same magnetic flux tubes. Then we plot these radar echo maps and the CNOVS plasma density measurement mapped over the magnetic equator. Then we see some similar, where where we have a radar basket echoes the plasma density depleted. This is the first orbit, then the second orbit. The CNOVs measure the sharp plasma density drop even during the solar minimum. So this result also suggests plasma bubble-like event. Plasma bubble are also generated in this solar minimum period. But again, scintillation activity was very weak. So the maximum event and so minimum event are somewhat different. This is a suggestion from this observations. Okay, this equatorial atmosphere radar was operated since 2001 until 2020. After that day, there's some hardware trouble by the lightning, but we have data more than 20 years. And this light gray color and black colors, light gray means the radar was operated mostly for the lower atmospheric studies. Then the black region means the radar was operated for the ionospheric observations. Then in the first half period, mostly the radar was used for the lower atmospheric studies. They only operated during the equinox seasons where the bubble activity is high. But after 2010, radar is mostly used for the ionospheric studies. So since 2010, almost 10 years, a radar was running only for the ionospheric observations. So we have a lot of data for the statistical analysis. So this is the statistical results of the plasma bubble occurrence. Sorted, first we divided into the 3 seasons, June, May to August, northern summer, and March and September equinox seasons. Then November, December, January, February. So northern winter seasons. Then this is a occurrence rate along with the F10.7 in the horizontal axis and KP index, 3 categories, weak, moderate, and strong disturbance. Then this March and September equinox seasons, this is well known that the bubble occurrence shows a positive correlation with F10.7, high solar activity case. We have more echoes. On the other hand, this June solstice seasons, the occurrence shows an anti-correlation with solar activity. During the solar minimum days, we have many echoes in these seasons. Then the December seasons, the occurrence is generally low, below 30%. So there's a clear difference according to the seasons and solar activities. And this is the occurrence statistical results for the occurrence time from 6 p.m., midnight, then 6 a.m. the next day. Again, the 3 lines show the 3 different seasons. And the March-September equinox, we have a high occurrence just after sunset, around 20 to 21 p.m. But in this June solstice seasons, the occurrence is high after midnight, 1 to 2 a.m. is the highest occurrence. Then December, November, December period, there's no very low occurrence. So this high occurrence in the after sunset is during the solar maximum period. And this high occurrence is post-midnight one in these seasons during the solar minimum time. And in December is very weak. So the difference between the June solstice and December solstice, this is something interesting because we are located in the equator. Then from the equator, the June solstice and December solstice should be symmetric according to the equator. But this is a very big difference between June and December solstices. The one reason is we are located in the magnetic equator, magnetic lower latitudes, back to this picture. We are in the southern hemisphere according to the magnetic equator. So this may be the one reason that's the asymmetry of June-December solstices. But we don't have clear explanation about the difference. So this is a similar picture along with the local time and F10.7 and the 3 seasons. again, this is a high positive correlation with the solar activity in this equinox seasons and the early local time. Then June solstice, this is a negative correlation with F10.7, and the occurrence peak is 1 to 2 a.m. So this is then the decimal solstice is very low occurrence. Okay, from the long history observation by our radar, we can collect this type of information, but we still don't have clear explanations of this difference. Even for the statistical results, we need to find the reason, the mechanism to explain this difference. And also the day-to-day variability, it is also the big questions. We cannot explain the occurrence. Why bubble occurred on that day, but nothing happened the next day. This is also the important topics. Okay, next half, we are going to the simulation studies. So simulation of plasma bubbles, this is the very beginning of the simulation studies published in 1976 by the NRL groups in the US. So this is very beginning, very simple paper title. Then in the abstract, they say that the irregularities produced by the instability grow on the bottom side of the F region peak, as predicted by linear theory. And then the irregularities non-linearly bubble through to the top side, where linear theory predicts no irregularities. As I explained in the beginning, top side ionosphere should be stable according to the linear theory. But observation shows that strong radar backscatters from the top side. So that's the reason why they started to do this work to explain the top side irregularities. So this is an image from this paper. Initially, they applied some initial perturbation in the lower ionosphere. Then the bubble started to grow, then reach into the top side. After 10,000 seconds, it takes more than 2 or 3 hours to make these results. Then this is a picture in their simulation paper. Then this image is actually from the paper Woodman-LaHosse, 1976. Then Woodman drew this image, this picture. They published the paper in the same year. But actually, this paper was published in November 1976, and this simulation paper was published in August 1976. But in reality, this paper was submitted before the simulation. And actually, the Woodman review paper says that the bubble idea was given from Woodman, then suggest the NR people to do the plasma bubble simulations. They have another simulation code at that time. Then during the conference, Woodman suggested to do the simulation. So this image, the Woodman drew this image only from the radar observations. He imaged this bubble before viewing these simulation results. Then the simulation studies confirmed that the Woodman's picture was very clearly correct, simulated by their code, simulation code. So this picture drawn by the Woodman was very innovative. I mean, it's very nice work. Then the simulation studies have been developed mostly by the NRL group, like 3-layer models. They successfully simulate these tilted structures of plasma bubbles. Then in the 21st century, the model is developed to have 3D structures. So this is a first 3D code by also the NRL group. The bubble generated in the equator, then penetrate or map to the north and southern hemisphere. Then also combined with the global models with a higher resolution in this sun-dusk regions, then try to simulate the bubble structures in the global simulation models. So we are trying to simulate. We also developed the plasma simulation bubble simulation code to see the very high small scale structures. So our concept of this not new already, our simulation model is to see the very fine structures inside plasma bubble. So our trial is to reduce the spatial resolution as much as possible. Now this is the initial setting of the simulation. It's very simple, only O plus and NO plus in low altitudes. Then apply some initial simple sinusoidal perturbation in the Pedersen conductivity. Then apply 0.5 millivolt per meter eastward electric field. And this is the simulation results. The initial perturbation is start to grow, then form these unstable structures inside the then penetrating the top side. Then this is a north-south view along the flux tubes are fully depleted, then reach to the like 20 or 20 degrees in northern and southern hemispheres. The focus on the bubble growth in the top of the bubbles. Now this solid line shows the equipotential contours. So this narrow regions indicates the strong electric fields in the eastward directions. Then this straight line is kind of streamlines of plasma flows. So the plasma flow from the bottom side going to the top side through this narrow channel of the bubbles. Then after penetrate into top PF peak density, the plasma bubbles start to going to be widened in top side. They start to bifurcate. They're forming these turbulent structures. Then after the bifurcation, the high density region in the middle is moving to the downward, while this depleted region is moving upward. Then these bifurcated structures are making another. Here we see some secondary instabilities. Again, this left bubble are pinched by these higher density regions, then just start to be kind of fossil bubbles. On the this right-hand side are still connected to the narrow channel from the bottom side. Then this bubble is keep growing, then making another turbulent structures in the wall of the bubbles. And this is the process of formation of the small scale plasma bubble structures inside the depleted regions. Again, this is a picture of explanation of the radiator instabilities. And now we try to consider the neutral wind effect for the seeding of the plasma bubbles. This is the linear growth rate derived from the linear theory. Here we have a neutral wind effect in the growth rate. So from the linear growth rate, upward neutral wind have a negative effect. The downward neutral wind have a positive effect. This is predicted from the linear theory. However, if we have a very localized neutral wind, for example, we apply some upward neutral wind in these regions, then we have this upward U drive the current U cross B directions, which is westward. But the current, this current flows only this vertical neutral wind regions. Then we have a charge separation here, like this. Then this electric field makes upward delta E cross B directions. Then as a result, this vertical neutral wind make this tilted, lifted structures. So this is kind of seeding of plasma bubbles. So we can imagine that this vertical neutral wind works as the seeding of equatorial plasma bubbles. Then we try to run the simulation applying the neutral wind with the two cases. The first case is Y large wavelengths. The second case is a small wavelength, but small amplitude. The first case is 10 meter per second vertical wind. The second case is a plus minus 5 meter per second. So very small vertical wind, but it has some impact for the seeding. So this is the first case, large wavelengths. Initially, the plasma density distribution is pretty flat in the very beginning. But applying the vertical neutral wind, the polarization effect happened. Then the plasma structure is slowly lifted in the central regions. And as a result, bubble structure is finally generated after 3,000 seconds or less than 1 hour. Again, the second case, the small amplitude, that's short wavelength case. Again, initially we don't put any density perturbations, but this vertical neutral wind start to produce initial seeding. Then finally the bubble formed in the top side. So vertical neutral wind, in this case, I put very simple case, but this vertical wind may be caused by the atmospheric gravity waves or any other neutral wind perturbations. So the neutral wind dynamics may be also important or ionosphere-atmosphere coupling is also the important topic. So this is the latest simulation with a much higher resolution, the 200 meter by 200 meter perpendicular to the magnetic field. So we can see the very turbulent structures inside the bubbles with a very high resolution simulation. Then we can estimate the spectral characteristics within the structures. So this is this background is a summary of the 4 previous satellite measurement. There's some spectral breaks, different spectral slopes. Then our simulation results also show some different spectral slopes. Very narrow spectral slopes, but suddenly change the spectral slopes around the very smaller scale structures. So internal structures of the plasma bubbles have 2 component power law structures, which is consistent with the previous satellite observations. So to see some impact on the scintillations, we need to go down to a little more higher resolutions. But we need a much bigger computers. But currently, this is the limitation. Maybe the next generation computers, maybe we are able to run the model more to simulate much shorter scale, like 100 meter or less than 100 meter scale structures. May be possible to simulate by our model. So now, finally, we like to introduce our recent trial to our simulation studies. The first topic is the combining with the global model with high resolution irregularity simulation models. We try to combine with the so-called Gaia model, which is the global atmosphere-ionosphere coupled model developed by Japanese colleagues. So it's kind of a multi-scale simulation models, combining the global model with the local regional models. Because only the regional studies, background condition is arbitrary, so it cannot be used for the forecasting of the day-to-day variabilities. On the other hand, this global model, they can simulate the day-to-day variability of the atmospheric conditions, but the resolution is very coarse, so it is not possible to simulate the plasma bubble occurrence within this global model. So the idea is to combine these 2 models in some way. So the first trial is to extend our plasma bubble simulation model to cover the whole longitude from 0 to 360 degrees. So in that case, we don't need to put any artificial boundary condition in the east-west directions. So high resolution bubble model regions in a narrow wedge, then connect from east and western side with a very coarse low resolution grid with 1 degree. grid resolutions. Then we try to simulate the 24-hour plasma electric field distribution from this simple model. Then it is somewhat similar to the Hikamaru drift observations and the vertical drift and zonal drift. Then we are able to simulate the plasma bubble. The resolution is very coarse, but using the global or whole longitude model, we can simulate the plasma bubble along with the global whole longitude electric field distributions. So this is the very first step to combine a couple with the global simulation model with this plasma bubble simulation models. Next trial is to try to simulate the storm time event. For example, this is a very famous event, the Halloween storm event. During the strong storm time, the equatorial anomaly is expanded to very high latitudes. For example, during the event, plus minus 30 degrees, due to the very strong penetration electric fields. And during that event, the plasma bubble impact can reach much higher latitudes. For example, over Japanese, really southern part of Japan, strong scintillation or strong large rotary activities are observed during the storm time. So to simulate this storm time event, we expand the top boundary of the simulation domain, including hydrogen ions. And the simulation covers up to 2,500 kilometers over the equator. Then in the latitude coverage is plus minus about 30 degrees, which can cover very strong bubble enhancement to very high altitude or to very higher latitudes. This is the results with and without the hydrogen ions. Without hydrogen ions, its simulation stopped when this depletion reached the boundary of the simulation domain. But we can keep running the simulation with the hydrogen ions when the bubble reaches much higher altitudes. Then this is our for this simulation, we applied very strong eastward electric field. So near the equator, almost depleted. The ionosphere is lifted to much higher altitudes. Then these bubble structures reach to 20 degrees or 30 degrees here. And this is a horizontal map in the zonal and latitudinal plot. Then this is the disturbed bubble structures can reach up to like 25 or 28 degrees in latitudes. So this is the some example that the bubble can actually reach up to this very higher latitudes when the bubble can reach over 2,000 kilometers over the deep equator. Okay, this is a summary. I skipped another observation. I focused on our radar site, but we are collaborating with many countries in the Southeast Asian countries, not only in Asia, but we installed several instruments in Thailand, Vietnam, Philippines, Malaysia, and collaborate with the researchers in these countries. Then the EAR in Indonesia is the core of the collaborations. Now we are proposing the new project in the equator to build the much bigger radar in Indonesia. About the simulation, the resolution is now down to the 200 meters. This is currently the record high resolution models. It may be close to the simulate directly the scintillation impacts on the GPS with the waves. So to understand the bubble occurrence, we have to consider the two factors. First is the preferred condition, like the plasma density distribution of background electric fields, and the seeding perturbations driven by maybe the gravity waves or another perturbations. So these two factors are the important things for future studies. So this is the reference of my work since 2004 up to years ago. Okay, thank you very much.
Yeah, Yokoyama-san, thank you so much for this very detailed description. And I think that if you look at the chat box, you have a number of questions.
Okay.
If you mind, can you answer them?
Yes, the post-midnight bubble is somewhat mysterious. Even I have no clear explanation. Yeah, sometimes it looks like a bubble. Sometimes it looks like a TIDs observed over the middle latitudes. So in that case, also the scintillation is very weak. So it's not the typical bubbles, but sometimes it looks similar. So it's I don't have clear explanation. Okay, the next question. Yeah. Okay, with no scintillation observation, for example, I made this observation 2019 across Africa, low latitude regions. What inhibits scintillation from occurrence while irregularity is still persist frequently? Yes, it's a good question. Yes, usually the scintillation is driven by 300 to 400 meter spatial scales. Then the radar bus scatter is only the few meter, 3 meter scales. So larger scale usually is kind of a cascade process from larger scale to smaller scales. So without scintillations, it's difficult to explain why only the radar echoes appeared without the middle scale structure, in the middle scale varieties. Yeah, it's also, I don't have clear explanation. Great. Then next, could you comment from your radar observation, what height irregularities generally occur at the low latitudes? Yeah, we measure usually the typical, the F region height, so 300 or 400. They sometimes like 600 kilometers when the bubble reach up to the higher altitudes. So this is maybe similar to the equatorial observations. It depends on the background plasma density distributions. Yeah, I have a question. When ionospheric disturbance happened, what is the impact on equatorial regions? And why this impact is different from other regions? Yeah, ionospheric irregularities are common in all latitudes, all the high latitudes and middle latitudes. But the plasma bubble, the biggest problem is they have a strong scintillation impacts on the radio wave. So the plasma density gradient is very strong. Then that may be a big problem for the navigations. Also, they have negative impacts for the HF radio wave propagations for the navigation for the airplane or ships in the oceans. So the impact for the navigation is much serious compared to the mid-latitude irregularities. This is, I think, the difference from the other latitudes. Okay. Another question, can it happen that the expansion of the EIA towards the pole and the equatorward expansion of the aurora over mid during so yeah, possible. But aurora expansion and the EIA expansion, it needs a very severe storm event. Yeah, it may happen like a Carrington type, very severe storms, but maybe recent years, like recent 100 years, we don't know such severe events. But maybe possible if we have a strong input from the magnetosphere. If I understand correctly, the vertical wind has a role on the formation of EPB. I know the other components such as zone and median have their own role on the formation of EPB. My question is, which component of the neutral wind can have dominant role on the formation of the EPBs? Yes, yeah, for the dynamo process, the eastward neutral wind is maybe the first very important thing. Yes, the vertical component is additional things. I think only the vertical wind, it is not easy to explain why the vertical wind happened. So maybe it's caused by the atmospheric waves like planetary waves or gravity waves. Then if this conditions are matched, well, then it may be the source of the bubbles. Yeah, but yeah, the meridional wind, like a trans-equatorial wind, will make asymmetric structures in the northern hemisphere and southern hemisphere. Then one theory says this trans-equatorial wind has a negative effect for the bubble growth. The asymmetric structure is not a good condition. So the symmetric structure has a positive effect. This is my understanding. Okay, another thing, which expansion is the primary cause of situation in the middle latitudes? Or expansion or the same, maybe the same question before. Oh, okay. Yeah, both case, yes. The situation over mid latitudes. Yes, bubble extension is another things. Also some TID like phenomena from the polar regions. It's also commonly observed over the mid latitudes. But situation is not so strong maybe from the TID, from the polar latitudes. Yes, so situation is maybe the equatorial expansion is more severe, I think. What is the best instrument to measure HWs? This is the no answer, I think. That's why we are easily say that's okay, this is like if we find the wave structure in the ionosphere, okay, this is driven by the gravity waves, because it is, it is difficult to find the evidence of the gravity waves in the ionosphere. So this is maybe bad habit for the researchers in the ionosphere. Okay, another thing. Did you include the effect of atmospheric gravity waves in your simulation? No, not included. The vertical wind is very simple. Just apply the vertical component. We didn't care about like dispersion relation over realistic gravity wave models. Just apply the vertical wind. It's very simple. But maybe that gravity waves are from the gravity wave component. So yeah, this is good things if you assume the dispersion relation of gravity waves into the another models. Yes. Okay, maybe I finished the question in the chat box. Thank you.
Yes, the question. Thank you so much. I think you enjoy answering the questions.
Yeah, thank you.
Right. I think that your lectures are very inspiring, and to many of us, you don't have a chance, to listen to your impression. But then I hope that we'll be able to invite you again, to come back to the talk. Before we leave I should mention that next month, I think the April 10th or something like that, Professor Tiger Liu of the National Central University will give a talk in this series. And Professor Liu, he will be speaking about, I think, about a number of things. I suppose one of the possible talk title would be on the possible precursor of earthquake, as displayed by atmospheric signatures. I mean, there's only one thing that he might be speaking. He might be speaking some other things. So please pay attention to the announcement, and welcome you again, to come to the talk. And I want to thank Professor Yokoyama for spending time giving the talk, and thank you so very much. Yeah, thank you again.
Thank you very much.
And I hope that you will be able to participate in this seminar in future also. Thank you. All right, goodbye. Goodbye. Thank you so much. Yeah, bye-bye.